It's not what I wanted. There we go. Alright, hello everyone. I hope everyone's doing well, and welcome. So here is my first online lecture, and I'm trying to keep it kind of similar to what we did in class. And as we go through this, as I learn more, this might change, but I think for now it'll be a good thing to do it this way. Okay, so if you have your notebooks, go ahead and get your notebooks if you're comfortable with taking notes. Let's keep it the same way, and we're going to continue with the same numbering of the pages. I'm going to keep my notebook here. You can keep your notebook there. So if you need to go get it, just pause the video and go ahead and get it. Okay, so we were on Unit 7, representing chemical reactions. But I think since we've lost so much time, we are going to go ahead and go on to Unit 8, and then the things that we need from Unit 7, I will just incorporate it in when we need it. Okay? So let's start with Unit 8, and this is Stoichiometry. Okay, and stoichiometry is actually comes from two Greek words. The first part means element, and the second part means measure. Okay, so what this is it's having to do with amounts of reactants or products in a chemical, or can sometimes be physical too, chemical or physical change. Okay? Oh, by the way, page 73. Okay, so before we can dive into that, we've got to do some review. And the review is going to be split up between this video and a few more. Okay, so the first thing we need to review is chemical equations. Okay, and specifically balanced chemical equations. Okay, this right here, this word, this concept, balanced, is essential for stoichiometry. Okay, so what is a chemical equation? Well, it represents this. It represents this. Okay, so let's look at an example. Let's do this. Alright, so this is a real chemical change that happens, and it happens when you run electricity through water. Okay, this is not evaporation of water, because if you evaporate water, you'd have liquid water turning into gaseous water, right? It'll still be water. So this is a chemical change in that you had what was once water turning into a totally different substance, actually two totally different substances here, hydrogen gas and oxygen gas. Right, so this is the breakdown of water into its elements. Okay. And what you'll see in a chemical equation, right, this represents this, what you'll see is an arrow, and on the left side of the arrow is the before picture. Okay, and then on the other side of the arrow is the after picture. Okay, in other words, this stuff up here turns into this stuff. Okay, and then we have a name for these. This would be reactants. And we had all this before. This is just a review. So if you got all this, it's good. Maybe you can put the speed up higher on the playback, just to make sure you don't miss anything. Okay, so we have reactants and products. Okay, and then we also learned how to draw the representation of these, the particle diagrams. And in order to do that, you'd have to understand what these are called formulas, what these formulas represent. So remember, the subscript tells you how many of the element that precedes it, how many of them you have in your particle. So this is all one particle, and it has one oxygen, right? There's no subscript there, so it means one, and you have two hydrogens. Okay, and then we have something called a coefficient. Coefficient tells you how many of these particles you have. So we have two of these H2O particles, which we all know is water. Okay, and then on this side we have, this is our particle. Ignore the coefficient for now. This is our particle. It's two hydrogen atoms. So our hydrogen, the way I drew it before, were these darker filled-in circles. So I'm going to draw two of them stuck together, okay, because a particle has atoms that are bonded together, and, or I should say molecule has atoms bonded together. Sometimes you'll have a particle that's just one atom. And then we have two of these, okay, two of those. And then we have two oxygen atoms stuck together. That's why we have the, once again, the subscripted 2 there. And there's no coefficient here, so that means 1. Okay, I'll put 1 in there really lightly, but we usually don't write the coefficient if it's just 1. It just makes it cleaner, less clutter. Okay, so if you noticed, there is no loss of atoms. So this is what it was before. We had 2 oxygens and 4 hydrogens. And this is what it was after the reaction. 2 oxygens and 4 hydrogens. No loss of atoms. So this shows the law of conservation of matter, which we know is real. The laws have been tested over and over again and verified. So we're representing truth here. Okay, so let's remind ourselves. Coefficients. Coefficients. This is how you spell it. Okay, and let's see if this shows up on camera. So these are my coefficients. Does that show up? Yeah, it does. Okay, and then the one, which really I don't write. Okay, those are coefficients. Okay, and why are these important for stoichiometry? Remember I said a balanced equation is essential for stoichiometry. That means these coefficients are super important. So why are they important? Well, they show the relative number of substances needed. Okay, and why do we use them in stoichiometry? So we can figure out how many product particles we can make from starting amounts or how many reactants particles are needed to make the products you want. Oh, I just realized you can't see that. Let me go down. Where did the camera go? Sorry guys, I'm still... Okay. Alright, so example. I need to go down more. So as an example, how many oxygen particles can we make, or we're not really making, see produce, let's say that. Can we produce if we broke down 4 water particles? Okay, so we go over here and we look at our balanced equation. According to this, if we have 2 of these, right, 2 water particles, we have 2 of those, we can make 2 hydrogen particles and 1 oxygen particle. So it's a 2 to 2 ratio. So for every 2 of these, I make 2 of those. Okay, I mean, other way. If for every 2 of these I want to make, I need 2 of those. For every 1 of these I want to make, I need 2 of those. But what if I had 4 of these? Well, that's double, right? So if we doubled everything, then we could see that if we had 4 of these, we would make 4 of those, but we'd only make 2 of those. Okay, so that's what stoichiometry is about. These are easy numbers to do, but that's really the idea behind it. It's kind of easy. They're ratios. Okay, so let's write our answer in our notes here. How many oxygen particles can we produce if we broke down 4 water particles? 2 oxygen particles. Alright, that's it. And I will see you in the next video.